Hello everyone, my name is Abhinav. I'm also a former PPLer and it's good to be back. So this session is about applications, and the first talk is by Professor Tom Quinn from University of Washington, Seattle. And this is one of the coolest collaborations we have. You'll see Tom usually has nice videos of cosmology simulations, so pay attention.
So I'll be talking to you about this cosmology code, ChaNGa. This has been a collaboration that's gone on for a while, so we've got a cast of thousands, both from the PPL here and people that have been in my group at the University of Washington. We call our group the M-Body Shop because we do M-Body simulations of a number of different astrophysical phenomena. The collaboration was started with funding from the NSF ITR program, and we additionally got funding from NASA. So today we'll start off by giving you a little overview of computational cosmology. We recently got a large allocation on blue waters, so I'm going to explain the scientific motivation for that particular allocation and running ChaNGa on blue waters. And then I'll go into some of the ChaNGa design, which is very similar to that Barnes Hut mini app that Harshita talked about, and some recent results both in terms of scaling and science publications before, and by talking about future work. So let me start out with the quick history of the universe. Okay, so obligatory plot. So on the horizontal axis is the age of the universe in a logarithmic scale, highly logarithmic scale. And then there's a very distorted distance scale on the vertical axis, attempting to show how the universe expands over time. A couple remarkable things. By observing the cosmic microwave background, we actually have direct observation of the universe when it was only 380,000 years old. What's even more remarkable is that the temperature fluctuations that we see in the cosmic microwave background appear to be an imprint that started as quantum fluctuations when the universe was less than 10 to the 32nd seconds old. And furthermore, I put up this particular slide because recent results from the BICEP collaboration have made observations of the polarization of the cosmic microwave background that have put observational constraints on the physics of the rapid inflation of the universe that is happening at this very early time scales. I think this is amazing that we have direct observational constraints on physics at the 10 to the minus 32 seconds in our universe. So that's remarkable. The other thing that's going on, of course, is that these density fluctuations eventually turn into the stars and galaxies we see today. So again, the large-scale structure in galaxies also reflects the quantum fluctuations at the very start of the universe. So, for example, this is from the Sloan Digital Sky Survey. It's a distribution of galaxies, and you see these voids. The size of those voids directly maps onto the size of the density temperature fluctuations we see in the cosmic microwave background. Again, going back to the very earliest times in the universe. Now, an issue with this particular picture is that we're not really seeing the underlying mass of the universe. These points here are galaxies, and if you zoom into one of those galaxies, it looks like this, and you're seeing a lot of very complicated physics going on. The light you see is generated by stars. It interacts with surrounding gas. It gets absorbed by dust, which are the dark spots here. It gets reflected off of other bits of dust. And so there's a lot of hydrodynamics and baryon physics that goes on in order to understand how those density fluctuations turn into this kind of picture. And we want to understand that collapse and that interaction because we hope to get some more clues about what the contents of the universe are. So that picture I just showed you is just a small fraction of the total energy density content of the universe. And so we're trying to use what we can see from the light to infer this mysterious stuff that we call the dark matter, which corresponds to about a quarter of the energy density universe, and this even more mysterious stuff that we call dark energy, which is the bulk of the energy content of the universe. And previous simulations have put constraints on what this dark matter is. For example, it can't be ordinary neutrinos. It needs to be something either more massive or more exotic, and I have a couple of candidates here. So in terms of computational cosmology, what we're trying to do is we're trying to take those fluctuations we see in the cosmic microwave background, which are 10 to the minus 1 part in 10 to the 5, and under the gravitational collapse, self-gravitational collapse, we create these galaxies. The centers of those galaxies are over 1 billion times more dense than the average density of the universe. And we want to follow that with enough fidelity to make these testable predictions. And so we need this highly nonlinear dynamic calculation. And just to give you a pictorial sense of the size scale we're talking about. So here's moderate scale structure. This isn't actually the largest scale structure in the universe. You see filaments and voids here. We zoom into the intersection of one of those filaments, and we've got a roughly round dark matter halo. We zoom in by another factor of 10, is the disk of stars and gas, which is the thing that we actually observe. And just to make the point that, well, first this point, there is essentially a fractal-like structure to the dark matter as we zoom into smaller and smaller scales, as shown in this particular simulation. And so that presents this computational challenge of covering many orders of magnitude in spatial dynamic range, cube that number to get the dynamic range in mass, but that spatial dynamic range also implies a large temporal dynamic range. The time scale for star formation, for example, is less than 1 million years, and we have to follow that for the age of the universe. And so that means that we can't be updating the entire large-scale structure of the universe at these tiny time scales. And this is further made a challenge because gravity is a long-range force. For example, the spin of our galaxy comes from forces from the nearby cosmic structure, which spans many tens of megaparsecs. And so you need to follow this information across your entire computational domain. And just making the point that we want to make predictions about this. If we had dark matter goggles, this is the structure we would see in the dark matter. You see these things are quite different. That's because the baryons obey the laws of hydrodynamics as well as just self-gravity, which controls what the dark matter is doing. How do you get the... So this is, all right, so this is a prediction from what the, this is theoretical model of what a particular type of dark matter would produce, okay? And so we have to say, well, does this create one of these if we put in the baryonic physics? essentially right. I mean, there is also hope that we might be able to detect this dark matter in, say, annihilation signals. You may have heard some announcements about seeing gamma rays from the center of our Milky Way, which may be an indication of the dark matter, a direct indication of the dark matter.
So you're saying everything's subject to gravity, but normal matter is, I guess, viscous, it flies into each other?
Exactly, yeah. Yeah, so yeah, technically the term is the dark matter is collisionless. It can pass through each other. It's very tiny cross-section. Ordinary matter, on the other hand, shocks and is subject to viscous hydrodynamic forces. So as well as calculating gravity, we need a method to calculate those hydrodynamic forces. We use this technique called smooth particle hydrodynamics. It's a method that works well when you have high Mach number and large density contrast. That's partly because it has this Galilean invariance. So if you have bulk motion, it does not change the equations of motion. It's also this Lagrangian method, so it actually follows the flow as you go into large density contrast. And the way to think of this is a Monte Carlo method for solving the Navier-Stokes equation. And the other thing is because it's made of particles, it makes a natural extension of the embodied techniques that we use for calculating gravity. So we use the same data structures to calculate the hydrodynamic forces as we do to calculate gravity. We do have to worry about star formation. Where do the stars form? This is physics that happens on the sub-parsec scale. So if we're to directly model this physics within cosmology, we're probably talking about Yada scale computing. So we already heard zeta, so I had to go one beyond, talk about Yada scale. But so we don't have that yet. So what we're doing, we have a subgrid model where we resolve things on scales of hundreds of parsecs, and if it's above a certain density threshold, then we have a scheme for turning that gas into stars. Stars go supernova, and so the energy from those supernova also affect the gas. They also do interesting things like inject metals. By metals, I mean carbon, oxygen. Sorry for the chemists, but this is what astronomers call metals. Yeah, hydrogen and helium are not metals. You know, chlorine, that's a metal. Neon, that's a metal. Okay. But the importance is that's the stuff you and I are made of. Okay. And so understanding this feedback is also important. And so we have this as a subgrid model in our simulation. We have been doing these kinds of simulations for a while and have been able to reproduce things that look like galaxies, starting from the cosmic microwave background fluctuations, both in terms of making disk-like things, getting the radial density profile right. So we think we understand how we can model galaxies. This is one galaxy. Here's the Hubble Space Telescope view of galaxies. This is a field for which many, many hours of the Hubble Space Telescope was used to get an idea of the population of galaxies in the early universe. So this is a snapshot of when the universe was only 1/10 its current age, and we see various types of all these little smudges are not stars. Each little smudge is roughly 1 billion stars in this picture. And we'd like to understand, why are these things red and these things blue? Why are these things disc-shaped? So understand the entire population. And so to do that, we need to model a whole piece of the universe with sufficient resolution to get that morphology. And this is the the goal of the allocation we have on blue waters is to understand these kinds of questions over an entire population of galaxies. And just so if you look at the largest scales, well, I wouldn't say largest, but large scales, the evolution proceeds like this. It loads. There we are. You start with the small density fluctuations. Things collapse under their own self-gravity. The collapse evacuates voids. The material from the voids tends to collapse into the filaments. As the filaments intersect, you get larger galaxies forming. If you have really good eyes, you'll see that these galaxies are forming stars, and there are supernovae going off that you'll see occasionally gas being expelled from the galaxies. But this is kind of the largest scale. We want to make sure that we understand the morphology of each of those galaxies that we form, because that's what we're going to compare with the Hubble Space Telescope observations. So here's a simulation that we just finished. It's also a simulation that the group here has been using for scaling tests. Here's a it's 25 megaparsec section of the universe. We zoom in again, we zoom in again, and we can resolve an individual disk of a galaxy. There are hundreds of these kind of galaxies in this box. And so what you should be thinking of when you looked at that at the last movie is that for each of those galaxies in that last visualization, we have this kind of dynamics going on, right? The galaxy is not this smooth buildup of material. It's actually a merging hierarchy of smaller lumps into larger lumps. And the dynamics of that merger, of those mergers, can be quite, well, interesting. As objects come in, you'll see that they incur a burst of star formation. For example, here's a little guy coming in. All right, first of all, it sort of disintegrates. The dark matter halo is still there, so as it goes by, notice there's a burst. All right, that's a star formation that's feeding back onto the gas. You notice as this guy went by, another burst happened, and of course, eventually this whole thing merges together with a very strong burst of star formation. This all affects the morphology and how the galaxy looks to us as we observe it with the Hubble Space Telescope. So question. Sorry, just get the scale. So that's the size of the box that we're looking at. All right, so this is a box that's 50,000 light years across. That's roughly the size of an individual galaxy, right? And we have hundreds of these things within this 80 mega light year volume. And the conversion from light years to megaparsecs is roughly a factor of 3.
How do you make those models and matches the Hubble telescope observation?
Well, all right, so there's two things. One is sort of verification, right, that we are following the laws of physics we think we're following. And, right, you run the standard tests. We're actually part of this collaboration of roughly 100 people where we're comparing different cosmological codes to make sure that we're getting the same results. So reproducibility is a big part of making sure that we're doing the right thing. And so as part of this collaboration, we're also comparing the star formation and the hydrodynamic physics that we put into these simulations. So running the standard test problems, comparing with other codes, is sort of that verification process. And then part of the prediction is, all right, do we make galaxies that look like what we observe? If we don't, then we've got some, we got some science going on. What's wrong with our model? In this one, it happens to be yes, because most of the universe is dark matter. So it's roughly 4 to 1 or 3 to 1, something like that, gas to dark matter in this particular simulation. Well, I'll talk a little bit more about that because, yeah, no, a very good point. In this particular simulation, we have a density threshold. If the gas is above a certain threshold, it forms stars on a dynamical time, and we've got parameters to adjust that. Basically, we're trying to match observed sort of density to star formation rates, ratios that we see in nearby galaxies. Yeah, yeah. Periodic, right? We're trying to model an infinite universe. Kind of hard to fit in a computer. The inflation, so the overall expansion of the universe is modeled. Okay. Yeah, the size of the box expands with the universe. Yeah. Yeah, basically we follow the equations for the expansion of the universe. All right, so that's what we're doing today. What we plan to do is to go down by an order of magnitude. So 2 billion today. Hopefully by the summer we'll start running a 25 billion particle simulation. And of course, with the corresponding growth in the size of our data sets, you asked about black hole feedback. That'll be the new inclusion, and also molecule formation, because we know that star formation is correlated to where the molecular gas is, and so that's to be is being incorporated as we speak. Just preliminary results here. This is a luminosity, star formation rate as a function of what we call redshift. And these are early times, late times, observations, this recent simulation. The fact that our simulation falls above observations is not too much of a worry because the telescope can't see every star, whereas in our simulation we can. So if it fell below, we'd be in trouble, but this is okay. We make this interesting prediction. The gray area is what we can observe, and we make this prediction that there's actually a rise in the star formation rate at very early times in the universe. We'll see if that bears out. So we've been doing all this with a code called ChaNGa. It's got a lot of features for cosmology, production code. I want to talk a little bit about its structure. Latency hiding is gravity causes a lot of communication, so hiding that communication latency is important. You've heard about over-decomposition. We do that by putting pieces of the tree, many more pieces than we have cores. But even within a char, we divide it into multiple work units, even dividing the off-processor gravity with against the on-processor gravity, and the hydrodynamics, and the periodic boundary condition calculation. We also, Harshita talked about this, methods that cause data requests are executed first so that those data can be gotten for future execution. Structurally within a processor, we've got many chars, and here's the division between local and global. Of course, the data that these things require tends to be the same. And so we avoid data duplication with a software cache so that if one tree piece needs some data, it's stored locally so that if a second tree piece needs it, it doesn't have to go for a second communication request. And here's how the calculation proceeds over time. So this is time and utilization of the machine. The gravity bits are in blue, shades of blue with remote work, local work, and periodic work. And then the hydrodynamics are in green with, this is essentially the continuity equation, the momentum equation, and the energy equation.
Question, why do we have that? Why do we have that?
Right here? All right, so in order for the pressure to be calculated, you need to know the density. So all the densities have been found, you can calculate the momentum equation. I've got to move along really quickly. Scaling to 500,000 cores with 12 or 24 billion particles is our recent scaling results. This has been due to work by Harshitha and Lukash, working on eliminating a lot of the fixed costs. And this was talked about a little bit during the last slide. Just point out some timings here. Without some of these optimizations, the domain decomposition and the tree build and the load balance in particular were taking a lot of time. After we've optimized it, in particular moved to a hierarchical load balancer, the fraction of time taken by the load balancing drops significantly, and that's allowed us to scale to 500,000 cores here. Seconds. And just a summary, these sort of fixed costs were important. That was for a uniform volume. I mentioned that gravity causes this large load imbalance, both because of the time stepping and the force calculation. This is not particle distribution, this is the distribution of the chars in space, colored by the load that each char has. And see, if you're in the center of a cluster, you've got a lot more work to do. The ORB domain decomposition that Harshitha talked about makes it look like this. Now the coloring is by processor number. Okay, and so you can see how the ORB tries to split things up, keeping things spatially local. However, you still have significant load imbalance because of the multi-stepping. So instead of having a nice even distribution of load around 1, we have the vast majority of the pieces in the small time step have 0 load, and you've got only a few hundred pieces to distribute. So that's a huge load imbalance. One of the things we've done to correct that is some intranode load balancing. So here's one of those heavy pieces. We've got a bunch of empty cores on a node, and so we just essentially do work stealing for that piece. Communication imbalance is another problem. This idle time here is because a lot of pieces are busy satisfying data requests. And so what we've done is duplicate those pieces so that we spread out the communication load, and now the time profile looks like this. So for these cluster runs, which are multi-stepping, only going to 130,000 cores here, but we're still getting a good fraction of parallel efficiency. If we also include the multiple time stepping, the fact that we're only evaluating forces occasionally for the slow-moving particles, we don't get as great a parallel efficiency, but you notice that the actual time can go down by a factor of 4. So in terms of utilization of the computer, we're not as great, but actually time to completion increases significantly. Okay, that's the scaling results, some science results. Here's a paper from last year where we're looking at the microwave signature of clusters. Here's a paper that I'm not an author on. It's a Nature paper that uses ChaNGa to model the interaction of a dwarf galaxy with our own Milky Way. And the point of the paper is that this collision that happened a few million years ago is responsible for some of the spiral structure we see in the Milky Way. Just to point out, the code is being used by others as well as our own group. And I already talked about this. We're going to be adding black holes, and we need radiative transfer to find out where the molecules are. We're experimenting with different forms of dark matter, but there's also the algorithmic improvements as well. And yeah, well, let me finish here saying, right, this has gone on for several years now, but we've been successfully addressing these computational challenges using many of the features of the CHARM++ runtime system.
Thanks, Tom, for the entertaining talk.
Do you have a sense for by how much the fidelity of these calculations would be improved by adding more particles? Well, you're already at 2 billion, right? But if you say went up by a factor of 10, from a physics point of view, how much would that improve the simulation?
So the reason we're going from 2 to 24 is exactly to improve the physics. That is, in order to understand the morphology of a given galaxy, we need of order 100,000 to 1 million particles in an individual galaxy halo. So as in this particular kind of simulation, as you increase the particle numbers, you can see smaller and smaller galaxies. So that's how the fidelity will improve. Correctly model smaller and smaller galaxies.
So you have multi-step and not multi-step, I guess. You have different modes you can run the code in.
Yeah.
So in the multi-step, you're subcycling the finer nodes of your ChaNGa tree at a finer time scale.
Right.
But you still need a globally consistent gravity background field.
Yes.
So you're solving the global gravity field at every single fine time step?
That's correct.
All right. How do you handle the mass being deposited on, as the coarse grid advanced in time and then you time interpolate?
Yes, so we rebuild the gravity tree every small time step.
Okay.